So what are carbon nanotubes? They are long, hollow tubes of carbon arranged in helical geometries to give the appearance of cylindrical chicken wire, giving a hollow, 2D nanostructure made up of a highly organized carbon mesh. The cylinder has a diameter on the nanoscale, conferring chemical consequences not normally observed with carbon materials.
While similar molecules called fullerenes were discovered by Roger Bacon in 1950, the credit for discovering carbon nanotubes as we know them today goes to Sumio Iijima and Donald Bethune, who discovered them independently in 1991. Although, technically the discovery can be traced back to Neanderthals with the discovery of fire, as carbon cages can be found in soot.
After their initial discovery and some years of research, carbon nanotubes have promising futures in electronics, quantum wiring, drug delivery systems, and even improving sports equipment, such as helping Floyd Landis win the 2006 Tour de France on his nanotube alloy bicycle.
This versatility is due to their properties. First, they're extremely strong. In fact, the Young's modulus for the strength of a single-walled nanotube is about 1 terapascal squared, making it 100 times stronger than steel and 1,000 times stronger than spider silk. Finally, they have excellent thermal conductivity along the length of the tube, but not across the diameter. For most architectures, the conductivity is 3,500 watts per meter Kelvin, which is over 100 times that of aluminum. Just don't breathe them in. If inhaled, they have been known to damage lung tissue. Yuck.
In addition, their electronic properties are determined by their shape and structure. Nanotubes come in a variety of conductivities, ranging from semiconducting up until superconducting under the right conditions. Granted, those right conditions are at about 20 Kelvin, which is too cold to be practical for day-to-day use. Conducting nanotubes like the Zigzag 90 and the Armchair 33 are considered metallic. A semiconducting nanotube has a finite space between the occupied and empty space. An example of this is the Zigzag 03 nanotube. More about these in a few seconds. For this experiment, we tested the theoretical conductivity of different chiralities of carbon nanotubes. We decided to run band gap calculations on Armchair 33, Zigzag 03, and Chiral 23 conformations via WebMO QChem software using the molecular orbital program with the 321G basis set.
And what exactly is the band gap? It's the difference in energy between the top of the valence band and the bottom of the conduction band in insulators and semiconductors. Crucial to the conduction process is whether or not there are electrons in the conduction band. In insulators, the electrons in the valence band are separated by a large gap from the conduction band, while in conductors, like metals, the valence band overlaps the conduction band. In semiconductors, there is a small enough difference between the valence and conduction bands that thermal or other excitations can bridge the gap. We can calculate this difference by finding the energies of the valence and conduction bands, commonly referred to as the HOMO and the LUMO.
As mentioned before, carbon nanotubes commonly exist as having either metallic or semiconducting properties. For reference, semiconductors usually have a band gap between 1 and 5 electron volts, while metals have notably smaller band gaps between 0 and 1 electron volt. The lower the band gap, the smaller the energy difference between the HOMO and LUMO, and the more conductive the material.
We found the Armchair 33 to have an energetic band gap of about 0.7 electron volts with 4 units, making it metallic by our standards. Additionally, we found the Zigzag 03 with 4 units to have a band gap of around 2.7 electron volts, making this a semiconductor, while the Chiral 23 nanotube with only 1 unit has a band gap of about 0.9 electron volts, acting as a middle ground between the two. As previously mentioned, different chiralities of the carbon molecules infer different absolute configurations, leading to various electronic structures. These various structures lead to the presence or absence of a band gap based on the position of the pz orbital relative to adjacent orbitals to form a delocalized band. Each carbon atom is covalently bonded to 3 adjacent carbons via sp2 molecular orbitals. The presence of a band gap coincides with the metallic nature of the carbon nanotube, a crucial aspect in future electronic equipment applications. The curvature changes in such a small diameter construct highly influences the ability of the orbitals to hybridize, thereby strongly affecting its electrical properties.
Nanotubes made with silicon carbon are popular, but for a greater amount of defects. These defects interfere with the passage of electrons due to the presence of a measurable band gap that must be overcome due to poor pz orbital hybridization. This compound, therefore, exists as a semiconductor. Boron-nitrogen nanotubes are similar to carbon-carbon nanotubes in that they are also held together strongly with covalent bonds. However, the sheets of the nanostructures are only held together by weak van der Waals forces. This creates such a large band gap that the energy needed to overcome it causes the boron-nitrogen nanotubes to act as an insulator as opposed to the carbon-carbon metallic nature. The boron-nitrogen nanotubes act as an insulator due to the presence of a band gap of 5.5 electron volts. These will always be insulators, meaning that the energy required to overcome the band gap is independent of the nanotube's chirality.
So, why do we care about any of these things? Small size, flexibility, and high electrical conductance of carbon nanotubes yields more efficient and advanced solar cells, smartphones, supercomputers, and biomedical devices. Such advances cover a spectrum of practical applications, including increased battery life and, more generally speaking, countless highly efficient conducting materials.